Now, let's dig a little bit deeper here and see if we can arrive at a more satisfying solution. Should villain decide to always fold, then we may decide to try and cheat him a little bit and start shoving a tiny bit more often. Let's say that we decide to shove 1% more often and see if villain picks up on this. By doing this, we're now making, we have 80.74, and let's recompute. By cheating here, we make 40 cents more. Should villain now pick up on this, he may decide to always call. Let's put the call action back on top. And we may now counteract this new strategy by shoving 1% less than equilibrium. And let's recompute. And now we're making 13 cents more than we made at equilibrium. Let's see. If villain always folds, then we can make an extra 40 cents by cheating. And if villain always calls, then we can make an extra 13 cents by cheating. Villain could counter his cheating strategy by choosing a counter strategy of his own, where he calls 40 times for every 13 times he folds. This would result in a calling frequency of 75.5%. Okay, let's fill that in. And let's change our own shoving frequency back to the equilibrium value. And compute. And now we'll see that not only is kings 0 EV, but 7-6 suited is also starting to tend towards 0. It takes a bit of experimenting here to get the exact optimal calling frequency for villain, since the 40 cent and 13 cent numbers are not the absolute exact numbers. There's some rounding going on here. Now I've already done that, and the correct calling frequency is 75.419%. Now, it's probably possible to deduce the exact frequency mathematically, but I decided to get it by experimentation. Anyhow, at this point, if we compute, we'll see that not only is kings 0 EV and 7-6 suited is 0 EV, but if we change either frequency, it will gain the player who does this absolutely nothing. To demonstrate, if we now decide to increase our shuffling frequency to, let's say, 100%, we make 80.74 now, and if we recompute, we make the exact same amount after as well. Let me change that back and compute. Neither player can gain or lose anything anymore at this point by changing his frequency, and this is the true equilibrium for this situation. And at this point, both hero and villain will have one combo that's exactly 0. Now, in many cases, you can achieve a similar effect with the ranges that are obtained by the software's Unexploitable shuffling tool. For example, in the hand we had in the first video, we had this spot. Let's again apply the Unexploitable shuffling tool to it. And let's now mouse over small blind range to see what's in it. Here we have 5s performing at minus EV. However, if we now apply a weight to these 5s, with the same process as described for a simplified range, we can find a similar equilibrium. I have prepared this previously. Let me just do a quick load. And let's compute. In this equilibrium, both hero and villain will have exactly one combo that performs at an EV of exactly 0. And let's have a look at another example. Let's again compute the Unexploitable shuffling range by setting a checkpoint and pressing the all-in button. And here we actually have 3 hands that are minus EV in the shuffling range. However, if we take the one with worst EV, which is 7-6 suited, and only shove that one a percentage of the time, again, by the same process, we'll arrive at an equilibrium. Let me just load the solution. And compute. And again, 7-6 suited turns to 0 EV, and the other 2 hands that were previously minus EV have now turned plus EV. As for villain's range, Queen 8 offsuit performs at 0 EV. Now, this process does not always apply. For example, here we have a shuffling range that is displayed in the article I mentioned earlier, where H6 offsuit is shoved 57% of the time. The software's unexploitable shoving tool, however, arrives at a solution that's 100% worse, and that uses 9-4 suited as the borderline hand instead of 8-6 offsuit. This is due to the card removal issue that I described in video 1. In this case, the shoving tool chooses a different configuration of the borderline hands and arrives at the result that, although it performs only 100% worse, it won't be easily used to get to an equilibrium solution. So, to summarize, the unexploitable shoving tool that the software offers is a fast and easy way to get very close to the optimal result. In many cases, with some effort, it's even possible to arrive at what appears to be a true equilibrium, although cases exist where this is not so easily achieved. But in the end, the tool is a very fast way to get a near optimal shuffle float range.